Hi students, let's talk about water potential. So remember, osmosis is movement of water across a membrane. And so osmosis, people think of it as like diffusion, but it's not really just diffusion. It's sort of like diffusion plus, because you have water, which is solvent for one thing, and two, you have that membrane. And the balance between this solvent getting moved and the membrane makes osmosis this really special phenomenon. And so a helpful way to think about this is to think about water in a U tube. So this is literally just a tube that's shaped like a U. And then in the center of the tube, there is a membrane. And only water can cross that membrane. So let's say we have a setup that looks something like this. So we have pure water on one side. And over here, we have a solution with some solutes in it. So this side would be hypertonic, right? We have more solutes, so according to what we've learned so far, water should go this way to the right and enter this side of the tube, and you can see the level of water has increased. So it's gone up, water moved. That's a way for us to visually see that happen. At the same time, it says osmotic pressure here because you can imagine there's more water on this side of the tube now. So there's like literally more weight pushing against this little tiny membrane. So there's actually pressure being pushed against that membrane. And that's what this means by this osmotic pressure. That's why, it's not like the water's going to keep going forever until it like spills out. It'll stop eventually because it's having to fight against that pressure. And not only that, but we can actually do reverse osmosis, right? So we could take like a little piston and stick it into that side of the U tube and literally squeeze the water through the membrane and squeeze it to the hypotonic side, which is crazy, right? And so this is why I keep harping on this idea that osmosis isn't just water diffusion, because this is like a very special thing that only happens with osmosis, that it's this careful balance between the amount of solutes in a solution and the amount of pressure. So this is why water potential is really helpful. Water potential is sort of like the most precise definition for which way water is going to move during osmosis. So what water potential is it's the potential energy of some solution of water compared to just pure water. And what it means by potential energy is like the potential of that water to cross the membrane, essentially. So like I said, the helpful thing is it's going to tell you which way water is going to flow during osmosis. And in this case, it's going to be dependent on not just the solute concentration, but also pressure. Or at least those are the two things we're going to worry about in AP Bio. There are some other factors like gravity and humidity, but that's beyond the scope of AP Bio. For what we need to know, it's just the effect of solute and pressure. Okay, so water potential, it's going to use this symbol called psi. It looks sort of like a trident. The symbol is actually named for Poseidon, who's the god of the sea. So this is spelled PSI, but you pronounce it like psi. And we measure water potential in units of pressure, such as bars or kilopascals, because remember we have like that membrane, and you can imagine that water pushing against the membrane. So that's why we measure water potential in bars or kilopascals. And then I think it's helpful to just sort of recall really quick what pressure is. So this would be from physics or from chemistry. So if we have some surface, all that pressure is just how often molecules are hitting that surface. So it's the amount of force applied to an area. So if we increase the pressure, if we're like smooshing how big this volume is, that's going to increase the pressure and make it more likely that that water will get pushed across the membrane and move via osmosis. Okay, so there are two, this is okay, so here is the formula for water potential. It's pretty straightforward, right? So the water potential is equal to the sum of the solute potential plus the pressure potential. So in other words, it's just adding up the influence of the amount of salts or sugars or whatever, the amount of solutes in the solution, plus the influence of the pressure that we are putting on the solution. So this equation is one of the equations that's on your AP Bio equation sheet, so you don't need to memorize it, but you absolutely need to know how to use it and like how to plug different numbers into it and how to interpret these types of problems. Okay, so a couple things we need to know just right off the bat is just by definition, we defined the solute potential of pure water is 0 because it has no solutes, so it has no solute potential because you've got to have solutes to have solute potential. So that's just the definition of solute potential. Pure water, we define as 0. And then for pressure potential, if you think of like a beaker of water just chilling out, we define that the pressure on that beaker of water would be 0 pressure potential. And then if we were to like push on the beaker of water or something like that, that would increase the pressure potential. But that's just, once again, sort of our default settings. And in these problems, unless it says otherwise, you can assume the pressure potential is going to be 0. Because if it doesn't tell you, it means that the problem is probably taking place in a beaker of water or something that is open and not getting pushed on. And that's why you can assume that the pressure potential is 0 unless the problem explicitly says otherwise. Okay, so that is okay, so we can define the pressure potential of this open beaker of water is 0, right? So we can think if we had this U-tube, if we wanted the water to move to the right side of this U-tube, how could we have that happen? Well, we could take a little piston and push down on this left side, right, and squeeze the water to the other side of the U-tube. That would do it. Or we could also take like a vacuum or something and suck water up on this side. Both of those things are possible. So pushing onto the water, we would call that positive pressure, like we're literally squeezing water across the membrane. And the negative pressure would be pulling up on the water and like sucking it out with a vacuum. You can have both positive or negative pressure. So when we get into some practice problems, you'll see that pressure potential can be positive, negative, or 0, but solute potential can only ever be 0 or negative. And when we get to the video on solute potential, we'll talk a little bit more about why. Okay, and that's just a quick introduction to water potential and how. Okay, so let's think about how can we actually use these water potential numbers to tell us which way water is going to move in osmosis. So we have a new definition now of the way that water is going to move by osmosis. And once again, going back to this is going to help you think about it, because in this example, when we push the water down, pressure or positive, it went to the other side, right? So this side where we were pushing on the water is a positive water potential. So it's pushing the water away to a more negative side. So that's going to be our definition of the way that water moves in osmosis according to water potential. So water is going to move from the region with a higher, like more positive water potential to a lower, more negative water potential. So here is an example. And when I say lower, I mean literally lower on a number line. So -10, if you have -$10, that's way less money than $3, right? So less on a number line. The way I like to think about it is, think about those pressures. If you were pushing on this side and pulling on this side, the water would go this way. It would go to the side with the more negative pressure. So it's pulling the water that way. Okay, so now we can summarize. We have 3 different definitions now of the way that water is going to move in osmosis. They're all complementary, but each one gives us like a little bit more sophistication. So far we've learned that water can move from low solute to high solute concentration. Or more specifically, we can say water goes from the hypotonic to a hypertonic solution. And now we can add on top of that water is going to move from the greater water potential to the lesser, meaning more negative water potential. And this last definition, the one in the box, is the one that wins. Always. That's like the best, most true definition. So if you ever have a problem where you are calculating the water potential, that is how you should figure out which way water is moving by osmosis. You shouldn't just look at solute concentrations, because if it's a problem that's making you calculate water potential, there's probably a reason why, meaning pressure is probably playing a role. Okay, and that is an introduction to water potential. In the next video, we are going to go through some practice problems.